Hey, so we've got fit an exponential curve to the points and sketch it. Okay, this is supposed to be super easy. So I told you guys in class that we have this shortcut, y equals, and then there's these blocks that you just have to fill in. T minus whatever over whatever. Okay, so this is the structure of what you're filling in. The starting value is 5. So the starting value you just pop there. And it has to be, if I tell you the points are 10, 10, and 3, 5, it's not just whichever point comes first in the question, it's whichever point has the smaller t value is your first point. Okay? And the growth ratio is 10 over 5. And our starting time was 3, and our natural time step is 7. So we would just write it as 5 to t minus 3 and 7. Okay, that's it. So fit the exponential curve. That's done. That was easy. Now let's go ahead and plot this guy. So we have the point over 3, up 5, and over 10, up 10. Okay, so it's going to look kind of like that. The important thing is to make sure it's growing and to make sure it has an asymptote at y equals 0. So the fact is you can't cross that axis. You can tell by looking at the structure of this problem that if t is minus infinity, this will go smaller and smaller and smaller, but it's never going to introduce a negative sign. Okay? So, I mean, I might even draw this a little bit more like that, you know. Okay, but this is good enough. But it should definitely not cross the axis. Okay, so then it says fit a logarithmic curve to the points 5, 3, and 10, 10. And it wasn't the same 2 points. You see, I flipped them. And the whole reason I flipped them was intentionally so you could just find the inverse function of the function you just drew. Okay, so rather than trying to start, you could do this. You could start with the general template for what it looks like if you're a log function and find all the unknowns, but that isn't the point. The point is to just find the inverse of this other thing, which was super easy to find. Okay, so you just say t equals 5 to 1 minus 3 over 7. Okay, and then we just want to solve for y. Okay, so how do we do that? So we just, I don't know if it's going to take a lot of time or not. So let's go ahead and figure this out. T over 5. Okay, looks like it's probably time for a natural log. Okay, we're going to have something like this going on. So then we're going to have something like this going on. Move these pieces around. Then you have y equals this expression. There we go. I think in the answer key I did it differently, and that's totally fine. So the answer key I said, first of all I said t equals, but it doesn't matter. I just didn't switch the variables, but then I ended up with t equals. So I'm going to write it as y equals over here so you can see they're the same. And this is the way it looked. Why is this the same? Well, because remember the conversion formula, love the one you're with, right? So we love natural logs. If we wanted, we could have taken log base 2 of both sides. And in that case, we wouldn't have the divide by natural log of 2. So this structure, natural log of t over 5 over natural log of 2, that whole thing is log base 2. So it's actually the same answer. Okay? So hopefully that oh wait, there's one more thing I'm supposed to do. It says sketch it may place both sketches on one set of axes. Great. So I don't really want to plot a second set of axes. So I'm going to just draw this. Now you can see this didn't work very well, right? I need to make sure 10, 10 goes on the line y equals x. So I can fudge it a little bit. That might not be 45 degrees, but it should work. And then this curve that I drew should cut through. There we go. So pretend like that's my original curve. And then I'm going to draw my other curve. So I'm going to draw this is 5, 3, 10, 10 is going to get recycled because it's actually, that's not typical, right? But you should be curving this guy in the other direction and make sure your asymptote for that guy's in the other direction. So what I'm going to look for, if you plot these two together, make sure you know this one's the log and that's the exponent graph. Make sure that the log curves look like that and the exponent curves look like that. So log curves is increase, but it's concave down, which we haven't totally talked about, but it's spilling water. And this is exponent is increase and it's holding water. Okay, so you're looking at concavity as holding water and spilling water, and it'll tell you. So for example, you can't have increasing but it's slowing down, and for the log curve you can't have increasing. Yeah, that's all. They're both increasing. Both curves are increasing, but log is increasing slower and slower and slower, so it bends down, and exponent is increasing faster and faster and faster, so it bends up. Okay, so those are the important points for that.